Okay, so maybe we get started. Okay, so it was done early, so we can finish early for dinner. Okay, so this will be the second lecture for the second half of this probability statistics and machine learning. Okay, so I think today I see more people compared to last week. So last this week we asked about what department they are from. So I heard AP and bioinformatics something, and also AE, CE. There are any other departments for the new guys? What department? I see. Okay, I see. Engineering should be okay. Any other? Then we move on. So I think lecture 7. So the last week was quite simple. We just talked about two things. Okay, so a little bit review. We just talked about two things. One thing is the data. Okay, so how you organize the data. So we're talking about the X matrix. A X matrix that is N by D. And I think you kind of understand this. And this X matrix can be different type of data. It can be questionnaire, it can be a video, it can be image, it can be language. Okay, so all those data can be eventually formatted as a X matrix. So that's the data. And the second part, we talk about the category of learning. Okay, so basically we're talking about three types: supervised, unsupervised, and reinforcement learning. Okay, so in general, I think it's very easy to differentiate given the task is very straightforward, so you can understand the task. So in general, from my observation, that the supervised learning method recent years is pretty mature. Okay, when I'm saying mature means that as long as you give me a task and as long as you have sufficient data, usually it's very straightforward to build a supervised learning task and to train your model. Okay, for the unsupervised learning, it's actually still ongoing. So there are many new tasks in the recent AI conference, AI papers, AI conferences. So it's still an ongoing type of research. And also reinforcement learning, we see very so basically reinforcement learning has a very good theoretical foundation, and also it has good application. I think usually this will be a separate subject, and because it's quite different and it's quite difficult. Okay, so we won't talk too much about the reinforcement learning because usually you have to learn it separately. Okay, because you have to learn reinforcement learning first and then deep reinforcement learning later. So that actually becomes one whole subject. Okay, so from today, I think we were talking about some methodology in the supervised learning because it has a very good and also during the methodology description, I try to give you a flavor of model analytics. Okay, so that you have some at least understand the notation or terminology when you want to analyze a machine learning model. I think that's the important part for a PhD. Okay, so using a machine learning is not a PhD stuff. Using machine learning, actually, the master student can do it. Okay, but how to analyze the machine learning method is actually a very PhD job. Okay, so today and I think half of next week, we'll be focusing on some of the supervised learning method. Okay, so I just try to pick some of the interesting and also famous methodology. So the first one we are going to talk about is the decision tree. How many of you heard about this? I think most of you. Decision tree? Yes, no? The name, at least a name you heard about. Or there's a sister method called random forest. I think this one is very commonly used in engineering papers because usually it provides a very good performance. Okay, if you're reading papers, you definitely see this. Okay, so basically, random forest is a lot of decision tree. So that's why it's called forest. Okay, so foundational model is decision tree. So the first thing we're going to talk about is this decision tree. Okay, so let's start from the problem. So let's look at this data set. Is basically a healthcare data set. We call it heart disease data set. Okay, so essentially this data has three features: family history and some blood pressure, and this one cross the tree. So essentially, you have this three dimension of the data, and then based on these three features, you want to identify whether this person has a heart disease or not. Okay, so essentially, this is your X, right? So this is your X. And remember that for the reinforcement learning, you need to have a Y. So this is your Y. Okay, so basically this is a 5 by D data. N is 5, D is 3. Okay, so three-dimensional data. Okay, so basically we want to, so I think based on the data, you know what we want to do. We want to build a machine learning model to diagnose whether a person has heart disease or not. Okay, so essentially, what we want to do is that we want to find a function h or f, no matter which letter you want to use. So this h function actually inputs the x data. The x is actually x1, x2, and x3. So we want to input x1, x2, x3, and this function needs to tell me yes or no, right? So basically 1 or 0. Okay, so basically, when we're talking about a supervised learning, or when we think that we are training a model, basically we want to find a h. Okay, so if this h is pretty good, then this h can perform like a doctor. Then can do make the diagnosis for the patient. Okay. So that's basically the idea for the supervised learning. So supervised learning is all about finding a function. Okay. So here, let's make a very simple. So actually, you have a lot of way to define this h function. So here in the decision tree, we just do a very simple if-else decision. So the if-else is based on a particular feature. So for example, let's say we decide on x1. We just look at x1. Okay, so we look at x1. So x1 has yes or no. So basically, this person has family history or does not have family history. Okay, so if this person has a family history. Okay, so basically, you can see that I'm doing like this. So given the data, given a new, you can imagine the input is x1, x2, x3 as as an input. Okay, so here I'm saying that I only look at x1. Okay, so if so x1 has two possibilities, it can be yes or it can be no. Right, it can be yes or it can be no. And then based on the yes or no, you can make the diagnosis. For example, here I'm saying that if you have family history, then I believe that you will have the heart disease. And if you don't have family history, then I believe that you don't have heart disease. Okay, so or you can do you can do vice versa. You can say that if you have family history, then you don't have heart disease, and if you don't have family history, then you have the heart disease. So basically, you have these two options, right? Or what you can do is that you can say both no, but both no is meaningless, right? So this decision does, so if else usually is yes or no. Okay, so no is useless. Then how do you decide whether it's yes, no, or no, yes. Okay. So this example I think is easy because it's our common sense that if you have family history, then you should it's high possibility that you have a heart disease. Okay, but mathematically, how do we decide whether we should put yes here or no here? What we can do is we call it majority vote. A majority vote. So here you can see that if you have the family history, there are 3 yes, right? So basically you have 3 data points for the family history, for the yes for family history. And then within the 3 within the 3 data points, 2 of them have heard this. Okay, based on the majority vote, I'm saying that yes, if this person have family history, then no. Okay, and if it's a no, then you can see here it's no and yes. So basically it's 50-50, right? If it's 50-50, you can choose yes or no either. Okay. Okay, so this is majority vote. So majority vote give you the higher success rate, right? So then we have this I think this is rule based, right? So we have this rule based decision. And one thing I forgot to mention, so this one is a supervised learning, I think you know that. And this is a classification problem, right? Because it's a yes and no, but you basically classify between yes and no. Okay, so this, to be precise, this we call it a binary classification problem. Okay, binary classification problem. Okay, binary means that you only 2 class, yes or no. Okay, if it's multiple class, we call it multi-class classification problem. Okay, okay, so you can see that based on the X1, we can have this rule-based decision process, and this is already a cluster. So this is already a model, right? And it's already a model, and basically we call this a classifier, rule-based classifier. Okay. Okay, and it has also its name. We call it a decision stop. Okay. Okay. So that's the background for the decision tree. So essentially, we have 2 questions for this decision stop. Okay. So the first thing is, basically here you can see that I just choose X1. So why we didn't choose X2, X3? So the essential question here is which feature you should choose for the decision. Okay. And then the second one is here you can see that we only use X1. Okay. So it's actually possible that we can further split. So here you can see that we use X1 to split the data into 2 parts. Then it might be possible that we can further split the data into more details using other features. Okay. So that's the 2 questions we want to answer. So why we stop at just 1 feature and how do we pick the features? So let's first answer the first question. Which feature should we use to split the data? Means that on which feature should we make the decision? Okay, so here basically we're talking about the splitting criteria. Okay, which feature should we use to split the data? Okay. I think this is easy to understand, right? So basically splitting means that you can see that this is a 5 data point. After you decide to use X1, you actually split the data into 2 parts. This 2 become a data set, and this 3 become a data set based on X1. Okay. Then basically the splitting criteria is you think of this as a function that can measure how good the splitting can be for a particular feature on a data set. Okay. So essentially, I think our goal is to make our classification accurate, right? So basically, the idea here is that we want to use a feature that can make our decision stop perform better. I think this is straightforward, right? We want to find a feature that can make, so after you're using the feature, the decision sum can be better. Okay, so based on this idea, we propose the first algorithm. So we can set the splitting criteria to be the error that you make. This example here. So we split on x1. Okay, so we split on x1, and then we say that if this person has family history, then this person should be yes, right? So it should be yes, yes, and yes. And if this person does not have family history, then this person should be no. Okay, should be no heart disease. And if you do this, you find that this decision sum has two errors. Okay, so you can see that it makes two mistakes. So that means if you use x1, then your error rate is 2/5. Okay, then let's try the second one. If we are using the second selection criteria, we are using this x2. X2 is more difficult because it has three different criteria. It has three categories. Okay, so that means we need to split the data into three parts. Or what you can do is that you can split the data to be, for example, low and medium and high. For example, let's do this: low, medium, and high. You can put medium high together, or you can put low, medium together. So it's okay. So let's just try this one. Okay, if it's low, then it's a no yes. Okay, so no yes. Eventually you can say it's yes, or you can say it's no. It's the same. You have one error. This you have one error. Okay, the medium high here. So medium is no, high is yes. So basically here you will say yes, and then you have one error. Okay, so in total the error rate here is 2/5. Good question. Okay, so low, do it again. So low here, you can see that it's either yes or no. So you do the majority vote is break even. So you can choose either yes or no as a result. It's the same. You eventually have one error. Okay, and here, median, high. So it's no, yes, yes. So majority vote, you vote for yes, and then you make this wrong. Okay, so two error. Okay, then we do this one. The x3, so normal and abnormal. So if it's normal, then no, no, yes. So this is no. So normal. If it's abnormal, it's yes, yes. So it's yes. Okay. So all yes, this is zero error. So this is 1/5. 1/5 error rate. So you only make one. So here you can see that it seems that x3 is actually the better one. Okay, so you should choose x3 as a splitting criteria, as a feature to split. Then you can achieve a better performance. So the motivation for this, I think, is pretty straightforward. So you always want to find the feature that can best differentiate the data, right? So if the feature is not very representative, then it's useless. We don't want to split on that. We want to find the most important feature to split. So this is another example. I think I don't need to repeat. You can try it by yourself. This one I think is pretty clear. X1 is useless, right? Because it's all one. It's completely useless. So I don't even need to calculate. It's clear that x2 is better. This one is useless, right? Because it's all one, so it does not have any differentiation. It's completely useless. Okay. So there are actually a lot of splitting criteria that has been developed in the machine learning community. And basically, you're just developing splitting criteria. You find this is useful, then it becomes a new machine learning method. Okay. So the training error one, I think this is most easy to understand, but it has a lot of issues. In reality, in practice, actually not too many people using this. Okay, so I just want to illustrate using this training error rate as a criteria, but this one is not very often used in the practice. So in practice, what I use are these two. They can use the Gini impurity. Okay, so you just search this one, and they have this measure. And if you are using this, so it's some Gini factor. Okay, so if you're using this, and then so basically they measure how the data is organized or not. Okay, so if you're using this, then this method is called cart. Okay, so it's basically a decision tree using the cart. Okay, and so today, what we are going to talk more is this one. So it's basically using a concept called mutual information. So if you're using this, then we're calling this method a ID3. So I don't know what's the name. Okay, so if you search on Google Wikipedia, you'll know why the name is ID3. Okay, but anyway, so basically it's we're using the mutual information. Okay. Okay, so let me talk more about the ID3 algorithm. Okay, so have you learned the entropy in your probability theory? Yes, no? Yes, yes, no? So Professor Jiang talked about this, no? Then in your undergrad, year 3, probability theory, I think you definitely heard about this term. So do you know what, so you know entropy, this term, right? In Chinese, it's called shang. Okay, so basically, do you know what entropy is used for mathematically? Or in thermal, this concept is also in thermodynamics, right? So in thermodynamics, what's entropy talk about? It's talking about the level of chaos. Okay, the level of chaos. Or you think of the level of randomness. Okay, so basically, entropy is a very good measure about the chaos. Okay. So here we have a formal definition of them. And so in the probability theory, there is a formal definition of the entropy. So the entropy is used to model, so it's defined for a random variable. Or if you don't understand what is random variable, you can just think of it, it's defined for a distribution. Okay, so it's defined for example, it's defined for a normal distribution. For example, I ask you, given two normal distribution, which one is more random? So this two normal distribution, which one is more random, or which one is more chaotic? So which one, A or B? B. Why? Because it has a higher variance, right? Then I think so maybe I ask you for all the distributions, distribution in 0 to 1, what is the most chaotic one? What is the most random one? So basically, I just so basically in a so I just find want to have the distribution that is in the 0 and 1. So you can define any distribution, right? You can have some distribution like this, you can have some distribution like this. So I'm drawing the probability density. Okay, so you basically can draw any distribution as long as their integration is 1. So it become a distribution, right? So which one is the most chaotic one? Or on the other way, which one is the least chaotic one? The least chaotic one, I think, is very straightforward. You just put all the mass at one point. So it's a deterministic distribution that all the weight is 1. Then it's very, very deterministic, right? Then on the other hand, which one is the most chaotic one? It's basically the uniform distribution. So uniform distribution is the most chaotic one, or is the most random one. Okay, good. So now you can see that if so basically the entropy basically says that if it's a high randomness, so it's more chaotic, then the entropy will be high. Okay, so maybe I interpret this formulation a little bit. So basically, it's integrating all the domain X, okay, all the support of the distribution, and so there no support. No, I think this is also a new term for you. A support. This is mathematical term. If you read any machine learning paper, you see this a lot. A support of a distribution refers to the domain, the value that it can be chose. For example, the normal distribution, the support of the normal distribution is a real. Support of normal distribution is real. It's the real from negative infinite to positive infinite. Okay. So for example, support for the uniform distribution, support of uniform AB is AB. Okay, so support basically is the range that the you can sample from, you can get the sample from. Okay. So here is basically says that I choose X from its support. I look at all the X from its support. And then I integrate or I sum. So depending on it's continuous or it's discrete. So I integrate the probability density of X times log Px. Okay, so a question, for example, if we look at 0 to 1, and if we concentrate on 1, so we put all the mass to 1, what is the entropy? So the entropy is, so in this case, the support is only 1, right? So what is Px? Px is 1. So it's 1 log 1. So it's 0. So the entropy is 0. Okay, good. Okay, so what happens if it's uniform distribution? Uniform distribution is basically yeah, you can I think you can calculate okay, so so you have to do the integration. Okay. Okay, so basically you just remember the more random of the distribution is, the high the entropy will be high. Okay. Okay. Yes. Okay. Okay. So let me give you several examples. So I talk about the discrete in continuous version, and it's a discrete version. then it's basic, and then it's actually easy to calculate. For example, given a distribution like this, you have you have, for example, this can be choose from 1, 2, 3, 4, and you have the probability mass for 1, 2, 3, 4. And what you can do is just, for example, P1, P2, P3, P4. Then what you will do is basically the sum of P1 times log P1 plus P2 log P2 plus P3 log P3 plus P4 log P4 and minus. So this is the entropy. Okay, for discrete, it's very straightforward. So just this equation. Okay, it's just P times log P. Okay, and you go over all the support, go over all the X. Okay, so this gives you the entropy. Okay, so here I think these are two examples. If all the elements are the same, then the support is zero. Sorry, the entropy is zero. Okay, and so one more thing I also want to mention. So here, the entropy is always non-negative. Okay, so this is always greater or equal to zero. So this is you can prove. You can do the proof. Why? Because the probability density is because this is a negative sign, right? And so you can calculate this one is positive, and this one if it's from 0 to 1, then this is definitely negative. So negative, negative, positive. So it's all definitely positive. Okay, so this is for a discrete version. So this is all. It should be always positive. It should be greater or equal to 0. Okay, always. Okay, then you can see here, this gives you the minimum entropy. Okay. So all the elements in this are the same. So this is the most, this is the least random one. Okay, so all the other situations is more random. Clear, right? Clear. Then another example. So for example, the distribution is 50-50. So you have two values with 50-50. Then how you calculate? You just do this, right? So 50-50 then is 0.5 times log 0.5 and 0.5 times log 0.5. So this gives you 1. Okay, so you can see it's higher. So I'm talking about random or chaotic. So on the other way, which means that if the entropy is low, means that the data is more organized. Okay, so if the entropy is low, means that data is more organized. It has some pattern. Okay, so you can imagine that if it's a uniform distribution, then there's no pattern, it's just pure random, right? If it's not uniform distribution, then at least it has some shape. This shape is a pattern, right? So that basically gives you some information. Okay. So essentially, you want the entropy to be low when you are doing, for example, you are doing classification, you are splitting the data, right? So what you want to do is that, so you can imagine that the original data is here. You do the split. Yes, you just use some criteria to split the data. And compared to this data set, you want these two data sets to be more organized. Okay, that means that you want to make these two data sets to have a lower entropy. Okay, so that based on this intuition, you can develop a methodology. You can develop the splitting criteria. Okay, so that is ID3. Okay, so in the ID3, we define a concept called mutual information. Okay, so the mutual information is very straightforward. It's basically talking about talking about the two random variable x and y. Okay, and it's basically we define this I. This I is defined as the entropy of y minus the entropy of of y given x. Okay, so I need to interpret this definition a little bit. Okay, so this one is basically that you're given a data set and you review what is x. The conditional x means that you know that what is x. Okay, and this one is the original data set, the entropy of original data set. So because you review some information, right? So we expect that this data set should be more organized. For example, you review that this is yes. So we compare this data set with this data set, then it should be more organized, right? So we calculate this I, which is the level of the entropy drop given x. The level of entropy drop given a x. Okay, so this we define as a max neutral information. So you can imagine that we want to find the x that achieve the maximum mutual information. Okay, so we want to choose the x that achieves the highest mutual information, so that we want to split on this x. Okay, maybe one example. So how do we calculate the mutual information? It's pretty straightforward. This one you know how to calculate, right? So it's just simple entropy. This one, you just need to calculate the entropy given the data has been fixed on x. And then you sum all the x, the outcome of x. Okay, so maybe a example. Okay, so this one, so what is hy? Hy is basically we calculate on here. We don't need to look at x, right? So it's basically even split. We just already calculate. So it's half split. So this gives you 1. So hy is 1. We don't need to calculate again, right? And then we need to we need to calculate this part. What's this one? So you can see here, it says that we want to look at the xd. So here we only have one xd, x1, for example. So we look at the x1. And then x1 has two options, has two choices, either 0 or 1. So then we need to look at 0 and 1 separately. Okay, so here you can see that we look at 1 first, 0 first. So 0, the probability is 1/2. So here is 1/2. So this gives you the probability of v is 0, right? In this case, so it's 1/2. And then it's basically h. We only look at the xt equals 0. So we only look at these two data sets because we already condition our xt equal to 0. So 0, 0. So it's a pure data set. So we know that this is 0. Okay. Similarly, we know this is 0. Okay. Then this mutual information gives you 1 minus 0 minus 0 equals 1. Question? Any question? Good. So later when you read the machine learning paper, you will see this kind of notation very complicated. But usually the calculation is pretty simple. Okay, so if you don't understand the formulation, you just try to read their code. Okay? Their code will be much more easier compared to the notation. So here you can see that the notation is actually pretty complicated. That's a common issue in the computer science community. They want to make their method not that straightforward, so that it can be easily accepted, easier to get accepted. Okay, so that's the issue in the computer science community. right? So you have to get used to it. Okay. Okay, so I think this one is strict. We did this, and then let's do another one. So this one, the x changes a little bit. Okay, so still well, this one we don't need to calculate, is one, right? Then we just need to calculate, for example, xd equals one. Then it's here. So it's here. Then basically we're talking about this one. This one is 1, 0. 1, 0 is half half. Half half it gives you 1, right? Then this gives you 1. Then you can see that the final result will be 1 minus half. Minus half gives you 0. Okay, so this is different. This gives you 0. This gives you 1. So you can see that giving you 0 means that this feature is completely useless. Okay, I think from here you can also notice that it's completely useless because no matter it can be 1, it's 1, then the y is 1, 0, and it's 0, the y is 1, 0. So basically, no matter whether xd is 1 or 0, it has no help for the classification. So then you calculate the mutual information and notice this is 0. Okay. But this one you can see that is pretty useful. Then you're having high mutual information. Okay, good question. Then I think it's pretty straightforward. So given a data set, what you need to do is just you look at different x and you calculate the mutual information. You just choose the high one. Okay, so here you can see that I have two data sets. You can calculate the mutual information for x1. So basically you calculate I, y, x1. So this x1 is completely useless. I don't even need to calculate this, basically 0. Okay. And the second one, what you need to do is, so first you need to calculate this one, hy. So hy is basically how many? 1, 2, 3, 4, 7, 8. So 2 out of 8. So 2 over 8 log 2 over 8. And 6 over 8 log 6 over 8. So this gives you the hy. And then you split based on the 0 and the 1 here, based on x1. So here you have a half-half. So this gives you 1. Right? And here you get all 1. This gives you 0. And then you can calculate like this. Okay, so here you can see that the mutual information is 0.3, so it's higher. It's a positive and higher. I think mutual information is definitely positive, not negative. So basically here you can see that is 0.3 is higher than 0. So you should definitely split on x2. Okay, then I think what you can do is very straightforward. You can do further, right? So first you choose x3, and then you have the new data set, and then you can calculate the mutual information again on the new data set. And then you can look at what is the improvement. And then you can further split. You can just keep doing this, and your decision tree will become, we call this, so in the tree, we call this a depth. So your decision tree will be deeper and deeper. So your decision tree can be deeper. And once it becomes deeper, so the classification become more and more accurate on training data. Okay. So you can imagine that if I give you infinite depth, I can almost achieve 100% accuracy in the training data set. Okay, I'm only talking about training. So because this is a training data set. And this is training. I'm not talking about testing. Okay. So you can just keep doing the splitting and keep using the best mutual information, the highest mutual information feature to split. Okay. So you can build this. You can develop from this decision stuff to the decision tree. Okay. Okay. So once you have this decision tree, for example, we already get this decision tree. Okay. And if we already have this decision tree, what we are going to use is, for example, I have a new data set, a data point. I have a new patient. This patient so has no high and normal. So what we can do, we just go from, this is a simple rule base, okay? So here we look at normal. So if it's normal, then we go here. Then we look at x1, so it's no, we go here. Then the decision tree says that it's no. Then we're done. Well, our prediction for this patient is that this person does not have heart disease. This is a testing scenario. So using testing data. Okay. So once you have the decision tree, it's very easy to use it. Just follow this criteria, and then eventually you'll get the answer. Right. So this is actually that basically means that after you train this data, you have this decision tree, and then you can easily use this as a rule-based approach. Okay. Okay, so I leave this data set to you. You can play with yourself. So basically, what here is the mode choice data set. So basically, you can if you travel, you can choose to drive by yourself, or you can take a bus, or you can ride a bike. And which traffic approach that you're using depend on these factors. For example, whether it's raining or not, and whether it's before and during the peak hour or not, and whether you are having a lunchbox or have a backpack or not, or whether you are tired or not. Okay, so this is a training data set. Okay, you can develop a decision tree based on this training data set, and then if in a new day, I find that there's raining and it's during the peak hour and you have a backpack and you're not tired, then I can predict which traffic method you're going to use. Okay, so that's the testing stage. Okay, so decision tree I think is pretty straightforward. So this is a pretty straightforward and simple approach because it's actually rule-based. It involves a lot of some probability theories, mainly because of this entropy. Okay, so most of the time in most of the package you are going to use, for example, use some library in Python or in MATLAB. If you don't specify, usually they will use this mutual information as a criteria. Okay. Only when you specify that you don't want to use this, if maybe you provide some justification or you have your own judgment. But this one in general works well. Okay. Because there's a lot of reason, but in general, is entropy. This concept is actually is pretty probabilistic. It has a lot of probability guarantee, and at the same time, it's actually a pretty I have to say it's pretty robust to noise. Okay, so in general, it's a good measure. Okay, compared to, for example, the accuracy. Okay. So basically, people like to use that. Okay, so later you'll see entropy many times. Okay, entropy is also closely related to the information theory. Okay, so I think it's a pretty profound concept that if you're interested, you just search on Google. There's a lot of discussion on this. Okay. Okay. So usually before this, it's basically master level or undergrad level. Okay. So all the context before, usually a machine learning engineer for master or a master student then machine learning they will learn. Okay. So as a PhD student, you should know a little bit more. Okay. So I just try to touch it, but usually this requires a lot of heaviness. I just give you a flavor. Okay. So the first concept, maybe you haven't heard about this. We call it a inductive bias. Okay. So inductive bias means that as long as you are doing a machine learning, you're developing a machine learning method, your machine learning method always want to predict do something that's you don't know the answer. Right? For example, here you have X and Y for training, but for testing, you only have X, right? So you always need to predict this Y in the testing. Okay. So this one you never have the answer. Okay. You just do the prediction yourself. Okay. So essentially, when you develop a machine learning method, you should have some belief or some principle. Okay. So basically, the inductive bias is the machine is inside this machine learning algorithm. Basically, it's a principle how it can be used to predict this unseen example. It's a principle. It can be used for the unseen examples. Okay. So the question we usually ask is, given a machine learning model, what the model is actually learning, okay, or what is the inductive bias of this machine learning model. Okay, so under what assumption or under what principle this machine learning model can learn, can generalize. Okay. So here is basically the inductive bias for the ID3 algorithm is a belief that we want to find this shortest tree that has a zero training error with a high mutual information features. Okay, so essentially so the inductive bias here is that we want if we can make a simple example given a two decision path. So there's one decision tree that you only need to make two decisions. You look at two features, you can make the decision, yes. And there's another one, you have a long chain, and eventually you'll say this is yes. And so this is two decision tree. One is shallow, another one is deep. Okay, and they achieve the same accuracy in the training set. They achieve the same training accuracy. So here I'm saying that both of them achieves zero training error. So which one you think is better? I think most of you may think this one is better. Why? Because it's simple, right? So then this is actually your belief. You believe that the simpler, the better. Okay, so this has no proof. Okay, so this has no proof. It's just your belief. Okay, so this actually comes from a very old, very traditional, classic Greek concept. This is also a principle called Occam's razor. I've never heard of this. The Occam's razor basically says that if there are two theories that can explain one phenomenon, to get us basically there are two theories can explain one phenomenon, then we always trust the simple one. Okay, well, we always think the simple one is the best, the better one. Okay, so this again, this is belief. Okay, this is belief. There's no guarantee. Okay, so here you can see that you always choose the high mutual information one. This is also a belief. This is not guaranteed, and this is not proved to be correct. Okay. So basically, you should always you should remember this. Most of the machine learning method they have this inductive bias. So their inductive bias says that they always prefer a simple model. Okay, so between two models, I always try, if the two model performs the same, I always like the simple one. Okay. So this is actually quite contradict from a lot of engineering model, because engineering model want to add things. They want to add one feature, another feature, but machine learning model many times they want to make uniform, make it one model to solve everything, like ChatGPT, something like this. Okay, so they want to reduce. Okay, so it's all from this very simple belief. Okay, if you're interested, I highly suggest you search this one, outcomes reason. Okay, so in general, so the first one, decision tree, there are several advantages and disadvantages. One advantage I haven't mentioned is because the learning part is actually pretty machine learning, but eventually the final result is very interpretable, it's rule-based. Okay, so that means this decision tree is actually pretty suitable for policies. Okay, so many governments, they like decision trees quite a lot. Okay? And also many engineering people, they like decision tree a lot because eventually you can look at how they make the decision. Okay? And then you can explain based on your engineering expertise, based on your domain expertise. Then maybe there's some interesting findings. Okay. So here we can see that I use classification as the example, but the decision tree can also be used for regression. It's possible. It's a little bit more complicated. I don't mention here. Okay, so it can be used for this regression and classification. So it's very generalized. And also, the decision tree is very compatible with the categorical or real value features. So no matter it's a 0, 1, yes, no feature, or it's a real number feature, it can be used in the decision tree. Okay, so the disadvantage, I think you also notice that the decision tree, the learning process of decision tree is actually greedy. Greedy means that I always find the current best one. Okay, I always find the current mutual information, the largest mutual information. So this does not guarantee to give you the best decision tree. It's actually a greedy approach. You know what is greedy, right? The greedy algorithm. Yes, yes. Okay. And another issue is that the decision tree, you can see that you can make the decision tree very deep and very deep. If it's very deep, then it's actually very easy to overfit. And then we have a new concept, what is overfit? I think you heard about this term, right? Well, overfit. So later, I think I can give you the formal mathematical definition of what is overfit. But here we just give you a description. Okay. So so in general, when we're talking about a machine learning model, there are two things can happen. We call it overfit and underfit. Okay. Overfit called 过拟合 underfit 欠拟合。Okay. I think the Chinese is easy to understand. Okay. So overfit basically means that your model is so basically you are training on the testing data set, right? If your model is looking at all those because your training data set has some noise and outliers, and if your model look at those outliers and noise and it learns too complicated, so it becomes a overfitting model. Okay, if your model becomes overfit, then there's actually it starts to learn the noise actually. Okay, when it's learning the noise, then there will be no inductive bias in your model. So it becomes a memorizer. Okay, memorizer means that it just memorize each of the x, and then your model knows that for this x, the output should be y. Okay, let me give you an example. So for example, you want to learning a regression. So here is your data. So from us, I think it's very straightforward. I think this is a good regression model. Okay, what happens is overfit. Overfit is that your model believes that those fluctuations has a meaning. Okay, and then your model will become something like this. Okay, so you can see that it becomes a memorizer. It starts to memorize the location of each data point. Okay, so because it becomes a memorizer, so it's actually losing the true trend of the model. Okay, that basically means that it's losing this inductive bias. Okay, so what is underfitting means? So underfitting is actually pretty straightforward. It basically says that the training data was not fully exploited. Okay, so basically you didn't learn sufficient information from the training data. For example, you just do a majority vote, then means that you put too much inductive bias here. So your belief is too strong that you didn't trust the data. Okay. Okay, it didn't capture the pattern of the data. It just captured the very rough pattern. It didn't capture the detailed pattern. Okay. So in general, given a machine learning model, you should always, so there's definitely something that you can adjust to make this model underfitting, overfitting, and just right. Okay, you definitely have some factors, some parameters that you can adjust. So it should be, anytime you learn a new machine learning model, you should be aware, first thing, what is the inductive bias in this machine learning model? And second thing, how, if your machine learning model, if this model it becomes overfitting, which parameter you can adjust to make it back, make it just right, or make it even underfitting. Okay, so there's always a parameter that you can change. Okay, then question, what in the decision tree, what is the parameter, what factors that you can change to make the decision tree underfitting and overfitting? I think it's very, for decision tree is straightforward, it's depth, the depth. Okay, so if you set a maximum depth, for example, I set the depth to be 2. Okay, so it's very easy to underfit. Okay, if I set the depth to be very high, then it's easy to overfit. So in the decision tree, a very important feature is basically the depth. Okay, so okay, so then let's talk about some more things. This usually is not in a master level machine learning subject, but I just want to mention. I'm using the slides that does not contain those many mathematical notation. It's just a little bit mathematical notation, but I try to give you the idea. Okay. So here you can see that we are so in the machine learning when you train a machine learning model or when you analyze the machine learning model, you actually you have different type of errors that you're looking at. You can run this model in different data sets, and then you have different errors. So basically, we can mathematically characterize those errors, and we can compare them. We can understand how they are different or not different. Okay, by looking at those, we can understand the performance of machine learning. Okay, so here, remember that we are talking about the supervised learning. We're talking about the finding the function h. Okay, so it's everything about the decision function h. Okay, so what we are doing in the training part is that we want to find a h such that we put the training data in the h, and then the arrow becomes the smallest. So we set it as we call it a training arrow. So here we call it training error rate. So it's talking about we are putting the training data into H, and then we compare the results, and then this error, we call it a training error. Okay. So then what's the next step? The next step is that we test this model. We use another data set, testing data set. We put the test in the H, and then we look at the accuracy. This we call it a test error. So when you want to use a machine learning, the test error, this one we never know in the reality. In practice. So you can imagine that when you use a machine learning in practice, actually you cannot calculate the test error because you don't know the answer. But here we can do it in our computer because we pretend we don't know the answer, but we actually know the answer so that we can calculate the test error. Right. So remember that you are training, you are in the training stage. What you are doing is that you want to minimize the training error. Okay, but actually you don't care about training error. The training error has nothing to do with the practice, has nothing to do with the reality. In reality, we care about testing error. Okay, these two can be different. Okay, then there's another one, we call it a true error. True error, we don't give a data set here. So the true error basically says that your H should be tested on all the possible data in the world. Okay, so basically your H should be universally good for all the possible examples in practice. So this we call it a true error. Okay, so this one only God knows. So this is oracle, so we never know. Okay. So only God knows what is a true error. So we never know this. Okay. This is basically the quantity we care about, but this is unknowable. There's no way that we can know this a true error. So what's our belief here? Our belief is that the testing data set is representative to the all possible examples, so that we can use the test error to replicate the true error. So that's our belief. Our belief is that the test error is similar to the, it's a representative data set for the all possible examples. Okay, then what is a counter example? You can imagine. For example, the situation changes. Okay, you're training on some camera, and then you're using a completely different camera. Everything changes. Then even though your model has a very good training error, has a very good training accuracy, has a very good testing accuracy, you use in practice, it becomes very very weak, or it becomes not it performs not good. It's mainly because your testing set, your training set is no longer representative. Okay, I think this is easy to understand, right? So we are talking about the transferability of generalization here. Okay. Okay, we'll talk about this later. Then what is overfitting? So here I can we can write down mathematical definition. The overfitting basically says that you have a good training error. Okay, you have already a good training error, but you notice that the true error is actually higher. Okay, so our idea, the ideal situation is that when the training error goes down, we believe that the testing error also goes down, and also we believe that the true error goes down. Okay, but in some cases, the training error goes down, but at the same time, the testing error becomes higher even, or the true error becomes higher. Then in this case, we call this a overfitting. Okay. Okay, so if I draw like this, so here I'm talking about the size of the tree. Okay, so I can make the tree deeper and deeper. So you can see that I think you can imagine on the training data set, as long as you can make the tree deeper and deeper, the training error becomes less and less, okay, all the way to zero. Okay, so here you can see that given the training error, given the size of the tree become larger and larger, the accuracy in the training data set is actually increasing, keep increasing. But the issue is that we don't care about the training accuracy. Okay, even the training accuracy being 100% is useless, right? What is useful for us is the testing accuracy, okay, or the real accuracy. Okay, so if you look at the test data, then you'll find that the test data start to drop, start to increase, which is good. But then you can say that it becomes it's even dropping. Okay, so that's a not good sign here. In general, we like this part. This part where we believe that your model is learning. It's indeed learning because you learn on the training, then you perform better in the testing, which is good. Okay, but later your model is even better in the training, but it becomes worse in the testing. So in general, we think this area, your model is memorizing. When it becomes memorizing, then usually it becomes worse in the unseen data set. Okay, we don't want our model to become a memorizer. Okay, we want our model to learn. Okay, so this is not good. Okay, because of this, so here you can see that we need to control the size of the decision tree, because here you can see that even the size becomes large, so your model becomes more complicated. Actually, the performance in the real world becomes worse. Okay. Okay. So for example, when we write a paper in AI in machine learning method, or for example, we talk about the machine learning method, no one will talk about the training accuracy because it's useless. Okay? No one care about training accuracy. So everyone care about your testing accuracy. Okay. So if you read most of the AI papers, they never report the training accuracy. Not useful. Okay. Even though I don't care it's 100%, 10%, it doesn't matter. What we care is how it can generalize to the unseen scenario, because in the future, when you use it, it's unseen scenario. Okay. Okay. So you can see that the decision tree can be easily overfitting. Okay. Then there's people are talking about a lot of approach to make the decision tree not that easy to be overfitted. So in general, you can see that the deeper tree becomes more complicated, okay, and it becomes easy to be overfit. And then there are several approaches to do it. Say, for example, you can stop splitting at certain depths, to fix the depths, okay, or you stop splitting when the data set is only contains some data, only contain, for example, 5 data points. Or you just look at the mutual information. If the mutual information is below something, you don't split. Okay. If you don't split, then you just take a majority vote for the remaining data set. You can see by doing this, you reduce the training accuracy. You reduce the training accuracy, right? You intentionally reduce the training accuracy, but those approach can potentially improve the testing accuracy. Okay, so in this case, you can see that your machine is too good at learning. Okay, so you have to limit its learning capability because it's overfitting. Overfitting means that your machine learns too much. Okay, so you have to limit its capability in learning. Okay, all those approach is the approach to limit its capability. And because you limit the capability, the training accuracy will be dropping. But the testing accuracy will be improved. Okay, good. Okay, so in particular, there is a technique in decision tree to prevent to overcome back this overfitting, which is called pruning. Pruning is basically you give me a decision tree. I can try to find those leaves that is not important. Then I remove them. Okay. Pruning, I think the Chinese is super easy to understand. 剪枝. Okay. And you just want to trim this tree to make it smaller. You just limit its learning capability a little bit. Okay, there's many pruning approach. I think I don't need to go through it. And if you go to a decision tree library, it will ask you to. So nowadays, those packages very easy to use. You just specify which splitting criteria you want to use, which pruning method you want to use, or anything that you just say in the package, and then it will train the model for you directly. You don't need to write the program yourself. Last week I mentioned about I mentioned about the package called. I show you. So sklearn. Okay, so for example, this one, so classification. So we have a decision tree, right? So it's tree-based decision tree, right? So decision tree, and then I'm using this decision tree classifier. So it has also a decision tree regressor. Okay, we haven't talked about how to use decision tree to do the regression. The idea is very similar. So let's say the decision tree classifier, you can see that you have the parameter you need to input. The first parameter is the criteria. Sorry, this one is using Gini. But it's okay. So Gini, entropy, log loss, you choose one. Okay, if you don't choose, then this package is using Gini. I think Gini is very similar to the entropy. So it's the same. And if I'm interested in what is the mathematical information, it talks about how to calculate. So we already talked about this one. And I also talk about the splitter. And here you can see that whether you want to define a maximum depth. Okay, if you don't want to define a maximum depth, whether you want to define the minimum sample, okay, the minimum data required to split. If the minimum data, so basically, in the data set, if you reach this minimum sample, then it will never, you will not split again. Okay, or this is minimal sample length. Those are all related to limiting the learning capability of the decision tree. Okay, and there's others. This is some transformation. Sorry, this one I think they can. This is also a practice. So basically, this says that how many features you want to split. It gives you some heuristic. For example, you can maximally split the square root of the feature. For example, you have 100 features. The maximum you can split on 10 features. There's just some heuristic people want to use. Okay. Okay, so that's how you define. You just define those, and then you can simply run this decision tree. So running the decision tree is very straightforward. What you can do here, you can see that you have an X data set, you have Y data set, and then you define a decision tree. You just fit for X and Y. Then you already train the decision tree, and then given a new data set, you just input the X, and it gives you the Y. That's it. 5 lines. You already finished the decision tree training. Okay. So nowadays it's super simple to use those, but you should understand those details. As a PhD student, you should understand why, not just use the model. Okay. Okay, so maybe let's take a break. We move to the second method. Okay.
My child, very close to
一般是会用这个 arrow 代替，对，因为这种相信它是好的。那么这可以吗？对，或者呢，你需要这需要处理。信任其实对，都不要现在对的，
Is it good to listen? EBS it's very true. But I have those
No.
Yeah. So
那我当时这个情况，
I did since last year, but my statements expired. And
This is
even to go, there is a entry rate.
okay, so it takes like now. Okay. So this
Yes.
yes, they Okay, so we move to the second method. So this one is even more simpler. Okay, so this is called KNN. I think I missed one page. So here, so for the decision tree, you can see that after pruning, it improves a little bit. Okay, but you can see that it's still dropping. And also, it seems that after pruning, the limit is still this size, and then you can see that the performance is still dropping, but it's a little bit slower. Okay. So in general, you can see that those techniques, they are helpful, but they won't be the rescue. Okay. The rescue is that you need to understand the model, and then you need to choose the best setting for this model. Okay, that's very important. And one thing I forgot to mention that uh, the so basically we are talking about the two things. One thing is task complexity. Another one is your model learning capability. Okay, so for example, if your task is simple, okay, for example, just a binary classification, usually a binary classification view as a simple one. Okay, so if the task is simple, then you should make your model learning capability similar. Okay, you shouldn't use a super complicated model, which means that its learning capability is very good, but you are using it for a very simple task. In that case, there will be overfitting. Okay, so the overfitting is all it's not. For example, for this task, this size is better, is optimal, but for another task or for another data set, maybe this size may be optimal. It actually depends on the data set. It depends on the task. Okay, so the general trend says that if your model is more complicated, then we prefer a complicated. Sorry, if your task is complicated, then we prefer a complicated model. Okay, then I think you can now understand why the ChatGPT is so large, because it's a very generalized solver. It can be used for multiple tasks. So it's a very complicated task. Okay, so this tool has to match. And you shouldn't use a very complicated model for a simple task. This is definitely not a good choice. Okay. But in reality, I think definitely in your domain, you'll find a lot of AI papers that using super complicated machine learning method solve a very standard problem in your domain. So in that case, we, from our view, it shouldn't be a good application. Okay, but it's actually easy to publish if you don't know those principles. Okay, because simple method usually is not appreciated. Okay. Okay, then let's talk about this one. KNN. This one is even simpler. Okay, so I think this is the simplest, one of the simplest machine learning method. Okay, have you heard about this? Yes? No? Yes? So okay, so a little bit. So basically, it's come from this idea. If you search on Wikipedia, this Wikipedia does exist. Okay, it's basically just one sentence. The duck test says that if it looks like a duck, it swims like a duck, and quacks like a duck, then this is a duck. Okay, so basically very straightforward. So if these two look similar, then their results should be also similar. Okay, so the KNN is based on this. The KNN basically says that we given a new result, given a new x, given a new x, what I need to do is I just try to find the most similar data in the training set. And then I just say that I just use the y in that data. Okay, so here we need to talk about what is similar? How do we define similarity? Okay, so in this vector space, it's very straightforward to define the distance, define the similarity. You can use Euclidean distance. Basically, you just measure the distance between the two vectors. Okay, or you can use Manhattan distance. You just use the absolute value. Okay, I'm not sure you heard about LP space or LP norm. Sorry, P norm. This is a mathematical definition. So this is basically 2 norm, and this is 1 norm. Okay, so basically you just use a norm for x minus x prime. Then you can define the distance between these two vectors. Okay, so I think this is easy to understand. Okay, for two-dimensional space, you basically just measure the straight line distance for these 2 points, x and x prime. Just measure the straight line distance. This is called Euclidean distance. And the Manhattan distance is basically this one. Okay, why it's called Manhattan distance? Because Manhattan is in New York, right? Manhattan Island. In the Manhattan Island, the road is something like this. Okay, so if you want to go from A to B, the distance is something like this. Okay, so it cannot be a straight line. It has to be this go this direction, or go x direction, go y direction. Okay, and the Manhattan distance from A to B is basically measured as x1 plus x2. Okay, so that's why it's called Manhattan distance. It's actually Hong Kong is also great. This is in transportation we call this a grid network. Actually Hong Kong is also great network. Okay. So no matter Manhattan distance you are using or Euclidean distance is basically the straight line distance. Okay, so you can measure the similarity, the distance between two vectors, and then we define this nearest neighbor method, which is, so you have a training data set. So in this case, they put n on top, so it's the same. Okay, so we have n data points from 1 to n, x and y. Okay, x1 and y1, x2, y2. So what I'm going to do, maybe some notation thing. Do you understand this one? What is arc mean? You haven't used this one? Okay. So you know what's the meaning of this one, right? Minimization of x effects. This is basically says that I want to find x such that the fx is the smallest. Basically, I want to find the x that achieves the smallest fx. This is the notation of this. Okay. So so a little bit more complicated, something like this: x in x and fx. It basically says that this basically says that I want to find the x in the x set such that fx is smallest. Okay, so we can, so say for example, we eventually find this x. We call this x star. So how do we define x star? X star is defined as, so basically what's the property of x star? And basically you have fx star is small or equal to fx for any x in this. Okay. Yes. So this is the property of your x star. Okay. Then if I'm just writing minimize x fx, so this one gives you an output. This output is fx star. Okay. And how do we output the x star? We write like this. This gives you x star. This is the definition of x star. Okay, so this is just a notation. argmin means that I want to find the x such that it achieves a minimum for fx. Okay, so remember this one, min x gives you fx star, argmin gives you x star. Arg means that I want to find the argument to make fx obvious. Okay, good. So this is just notation. Okay, so once you understand this notation, then you can see here, I try to find the I from 1 to n such that the xi is the closest to x prime. X prime is the new data. X prime is the testing data. Test data. So I want to find the smallest distance between xi and x prime, and then I do argmin. So here we have the I star. So I define as this notation. Okay. Then what's our outcome? Our outcome is just y I star. Okay. So this is mathematical notation is complicated. So I think it's very simple. If we just if I just describe the algorithm, it's very simple. So here you can see that I'm having x here, I'm having y here, right? Sorry, this is I think this is x1, x2. Sorry, this is x1, this is x2, and we have either to be positive or negative. And so positive, negative is y. Okay, so say for example, I have a new x. I have a new x here. So this is our x prime. Location is not good. Let me choose another one. X prime here. X prime here. Okay, so I'm asking you, using the nearest neighbor, what should be the y for this x prime? It should be negative, right? Why? I'm just following this algorithm. You can see that I'm comparing this data with all the existing data. So I'm looking at the distance from this point to here, from this point to here, from this point to here, from this point to here. And I notice that this one is closest. Okay, so because this one is closest, then this is negative, then this is negative. That's it. This is called nearest neighbor. I just trust that our new test data is similar to its nearest neighbor. Okay, this makes sense, right? So it's reasonable. And because of this, then you can actually draw some decision boundary like this. We call this is also a terminology. We call this a decision boundary. So the decision boundary basically is that between on the two sides of the decision boundary, it can be different. So here you can see that if your data is here, then it's negative. If your data is here, it's positive. If your data is here, it's not negative. If the data is here, it's positive. Okay, so how do you draw this figure? It's actually pretty straightforward. You just connect this to find the middle point and draw the perpendicular line. Okay, so this figure, this figure has a name. If you want to draw it by yourself, you just search this one called Voronoi diagram. This is called Voronoi diagram. This is very useful for the nearest neighbor. Okay, have you heard about this? No? Yes? Okay, but yeah, now you know, you just search and there will be a Python package that you just provide the points and then the Python package can directly draw this figure for you. Okay, so this is called Voronoi diagram. Okay, so then I present the nearest neighbor model. And I think you notice one thing. It's very interesting that this nearest neighbor model, there is no training. And it didn't train anything. You just keep the training data set. This is already the training. Okay. What you need to do is you just compare the distance and you use the nearest one. So this is actually one of the simplest approach that is used. But this one has a very profound impact, actually. This is very useful in many cases. Even though in many real-world applications, people are still using the nearest neighbor. For example, in the for example, you are a new user for example, you just register the Weibo or register the Facebook, the Facebook, and then the Facebook will use your registration information and compare with the existing users, and then they find the nearest neighbor of you, and then they just believe you like the same thing as this person, and they will recommend all those similar things to you. For example, they find that you are with this another person is very close to you and the same age, same gender, same level of income, then the social media will directly recommend everything that's recommended to him to you. Okay, so it's actually pretty effective in many cases. Okay. So here you can see that the nearest model is no training. Okay, and because there is no training, then it's zero training error because a data point is always its own nearest neighbor. I think this is very easy to understand, right? So, and I think I just mentioned, right? So as long as this is a machine learning method, you should have something to adjust the overfitting and underfitting, right? So here you can see that clearly this is overfitting because it's zero training error. Okay, so how can you make it underfitting for the nearest neighbor? The idea is also straightforward, right? So you just don't look at the nearest one. Maybe you look at the nearest two, right? You look at the nearest three. Okay, that's why we call it k nearest neighbor, KNN. Okay, so basically, what you can do is that you can look at the k nearest one. Okay, so we'll talk about that later. So a little bit more here. So here, I just give you a flavor of some proof. Okay, so later if you are writing papers, if you actually using a machine learning method, if you can write something like this, it will be definitely helpful for your paper to be accepted. Okay, and also it can make your paper more sortable. You are not just using your a machine learning model. So basically this part we're talking about. We're trying to analyze this machine learning model from some mathematical perspective. So here we are trying to develop some proof related to the generalization capability of nearest neighbor. Okay, so here what I'm claiming, what I'm saying that based on my description of the nearest neighbor, for this methodology, if you have infinite number of data, then the true error rate, remember this is error of h. Okay, the true error rate is always it can be bounded. We say this is bounded by 2 times of the classifier rate. That means that if your classification error is 2%, then the true error rate is at most 4%. Okay, so if you can write some, so basically in the machine learning community, there's a group of people, they want to analyze the performance of different machine learning methods. They need to write some proof like this, so that you can analyze how good or how bad your model can perform under some circumstances. Okay, but usually if you are learning a machine learning as a master student, you never learn this part. Okay, but if you're a PhD student, you want to know more detail, you should at least read some of the proof. And from the proof, you can roughly understand why this model performed well or why this model does not perform well. Okay, this actually gives you some hints. Okay, so here you can see that we have a lot of assumption. We say that this is a binary classification. We will have outcome 1, 2, and all those data points are IID. So this is very independently draw independently from the same probability distribution. This is called ID, independently identically depend. What is D? Okay, and so basically here we are saying that the label can are stochastic, and the label is some we define as a pi. Okay, so basically you give a x. I have a pi function. This pi function can convert this x to a probability of this data being 1 or being 0. Okay, and then we assume the pi is continuous. Okay, so then we have this one. We can see that if n is infinite, okay, if you have infinite many of data, then you give me x prime. And if I look at the closest to x prime, this will be so basically this one is prime x prime because it's itself, right? And then I'll have this one. The probability will be also the approximating to this pi x prime. It's because you have sufficient number of data. The probability will also equal. So this is based. I think this is based on a large number, a law of a large number. Okay. Then what I can do is that I can write the error rate of the classifier H. So what's the error rate? How do you mathematically write the error rate? It basically says that is the expectation of this x. It goes through all the x prime, the possible x prime, and the h x prime. So I put the x prime into the classifier, but the result does not equal to the real answer. Okay, and this I refers to the indicator function. I think that you know this, right? Indicator function. And this one equals to the probability of h x prime not equal to y prime. So this equals to the probability of your classifier becomes wrong. Okay, and your classifier becomes wrong. There are two situations. One situation is that your classifier predicts 1, but the answer is 0. And another one is your classifier predicts 0, but your answer is 1. So this probability equals the sum of these two probabilities. Okay, and then you can further write. So what's this probability? This probability basically says that the y is 0, means that this one is this one is 1 minus pi. And then you have the x equals 1, then it's this one. Okay, so here so basically the other will wrong. And then you just see here, when n goes to infinite, you have this, then you can just plug in. So you can see that this equals to here. And I do a little bit relaxation. So this one equals to this one, smaller equal to this one. And this is particular the error rate of H, the error rate of H star. Okay. So then you have the proof. The proof is basically says that the error rate, the real error rate, smaller and equal to this one. Okay. So I just quickly go through. I just want to give you a flavor that if you can do this type of analysis, then means that you have a very deep understanding of this machine learning model. Okay. But usually for different machine learning model, there will be different proof. Okay, the proof technique is completely different. Okay, so this part we cannot go through a lot, but once you choose the machine learning method you use in your paper, please try to look at the assumptions and try to look at whether those are reasonable or not, and try to make it more suitable for your settings. Okay. So basically, this here can see that we complete the proof, means that this has some interpretation. It basically says that half of the classification information is actually contained in the nearest neighbor. So basically, you just use the nearest neighbor, you already achieved 2 times of the error, right? So it means that there's a lot of information actually contained in this nearest neighbor. Okay. So as I just mentioned, so you once you so as for a machine learning method, you definitely need to have some parameter to tune, so to make it overfitting and underfitting. So in the nearest neighbor is not a good machine learning method because there's no parameter. Then people come up with this idea K and N. I think now it's very straightforward. K is basically the K nearest neighbor. Okay, so basically, if you so we basically what we are going to do is that we find the K nearest neighbor, and then we can use the most common label from this K. So basically, we do a majority vote. We do a majority vote for this K neighbors. Then we get the final answer. Okay, so I think it's easy to understand. Okay, for example, for this data point, I choose the nearest three. I think it's this one, and this one. Okay, then two positive, one negative, majority votes. Then I believe this is positive. Okay, and in many cases there might be a tie. It means that there are two positive, two negative. Okay, if there's a tie, there's a lot of technique you can use. For example, you can weight the vote by distance. So, for example, there's one point that one data that is very close, I trust it more. Okay, I think this is the easy one. Or there are some technique says that you just remove the vote from the furthest one, or you just add one more. Okay, or you just try different distance matrix. So it's basically just some approach to break tie. Okay. Okay, so K nearest neighbor, it gives you something like this. Okay, so here you can say, this is K equals 1. And sorry, I forgot to attach the K's to. So maybe I can directly ask you. So this is K equals 1. So for K equals to 2, can you imagine how the decision boundary will change? So basically, when K grows, the decision boundary will become smooth. Become smooth. You can see this one is not actually not very smooth, but if the K grows, you can imagine that the decision boundary will become more smooth. Okay, I think this is easy to understand. And from another perspective, when K grows, this basically means that your model becomes less overfitting. Okay, it becomes more underfitting. Means that you are introducing more inductive bias to the model. Okay, you are introducing more inductive bias means that you insert a lot of principle, your trust, your belief in the model. Then this model becomes smooth. Okay. So here, the KNN, what is the inductive? So this is also the question. So what is the inductive bias? The inductive bias in the KNN is very straightforward. So basically, it says that if the points they are similar in features, then they should be similar in answers, right? The duck test. If all the features are similar, then their results should be similar. Okay, similar points should have similar labels. This is the inductive bias in KN. This is very clear because you didn't learn. You just use this inductive bias to get the answer. Okay, and again, this is your belief, right? Similar points have the similar label. This is just your belief. Okay, I can create a data set that's completely different from your belief. Okay. But why this is always a good approach? Because we believe that the nature is continuous. because the nature is continuous, our world, our living world is continuous, then many things that are continuous, so your this belief holds. Okay. I think you can then imagine what type of data is not suitable for KNN. If there's some data that has sudden change, it's actually not a very good data for the KNN. KNN is very good at smooth data, or very good at continuous data. Okay, so here you can see that setting k, k equals 1, basically you have a very complicated very complicated decision boundaries. Okay, this is overfitting. And what happens when k equals n? K equals n basically means every time you look at all the data. So the k equals n basically is a majority vote. It goes back to the majority vote. And you always predict the most common label. This is definitely an underfit. Okay, so you choose k between 1 to n, so you're actually adjusting whether your model is underfit or overfitting. You are adjusting your model's learning capability and the level of inductive bias. Okay, so you can see that the k controls the complexity of the hypothesis test, hypothesis set. This is a new concept to you. So maybe I explain that later. What is hypothesis set? Okay. So basically, k affects how well the learned hypothesis can generalize. Okay, so there are also some proof in KNN says that if the k is basically some function of n, so basically it says that based on the number of data, you can choose a k. Okay, and those proof says that your k, if n goes to infinite, your k should also become infinite. Okay, and the speed of the k, growth speed of the k should always be lower than n. Okay, so for example, your n, then your k can be like square root of n. Then this still goes to 0. Okay, so here is just some heuristic. Say, for example, I can choose k to be square root of n. This is a notation, nothing to do with our lecture, but if you, in case you just don't know what's the meaning of this one. Don't know this one. So there are three words. Okay. Now this is also mathematical notation. Okay. So this one is rounding. Okay. This is rounding. This is, we call it floor. Floor means that we round down. Okay, 3.3 we round to 3. 3.9 we round to 3. This is called floor, round down. And this is called ceiling, round up. Okay, so rounding is basically you round by, if it's 4, then round down. If it's 5, round up. Okay, floor is always round down. Ceiling is always round up. Okay, so just mathematical notation in case you don't know. Let's put it here. Okay, so here you can see that no matter it's decision tree or it's KNN, there's always a fundamental question is to choose some parameter. So basically, you should choose a proper complexity of your model that is suitable for the data. Okay, so in the decision tree, we are talking about the size or depth. In the KNN, we are talking about K. There are many things. For example, in the neural network, we are talking about the depth or the new number of neurons. Okay, in the random forest, we are talking about number of trees. In the support vector machine, we are talking about the margin. Okay, in the gradient boosting, we are talking about the number of these boosters. Okay, so different machine learning method or in the ridge regression, we're talking about lambda. So in most of, actually in all the machine learning model, there's always a parameter or multiple parameter that can help you to tune your model, to tune the complexity of your model. Okay, then there will be a universal question: what is good? Okay, how do you tune? So this gives you another topic of, we call it a model selection. Okay, so no matter what machine learning model you are using, you should always know how to do a model selection. Okay, so then we move to this part. This part is not a methodology; it's a concept. So there's some analysis here. Okay, so maybe let's take a break. Okay, so let's take a break. We'll move to this model selection. Okay, so we move on. Okay, so so we talk about model selection. So this I think is very important part. So later when you use different machine learning model, you should always use this part. Okay, so this part is pretty important for developing a valid machine learning model. Okay, so so here the first thing we want to highlight is that usually for a machine learning model, we are talking about training a machine learning model, right? So we're always talking about training a machine learning model. So when we are talking about training a model, what we are doing, we are actually searching for parameters. Okay. So for example, the decision tree actually says that which feature to split. This is the parameters. Okay, and KNN does not have parameters in the training. Okay, so for example, neural network, it has a weight in the neural network is parameters. So in a machine learning model, usually we will have two types of the parameter. We call it parameter and hyperparameter. Okay. In most of the machine learning, you will have these two types of parameters. Okay. So how do you differentiate parameter and hyperparameter? The parameter basically is a parameter that you can train using the training data. Okay. The hyperparameter is some parameter you have to define before the training. Okay, for example, the decision tree. If you want to set a maximum depth, this is a hyperparameter. Okay, so what is the maximum depth? Or what is the maximum size? This is a hyperparameter that you need to set before. Okay, and once you set the hyperparameter, then you can train which feature to split in the training set. Okay, and in the KNN, you don't have parameters because there's no training. Okay, but you have hyperparameters. K is a hyperparameter. Okay, similarly, for example, neural network. The neural network, you need to decide how many layers you have, right? The number of layers are hyperparameters, and the layers can be trained using the training data set. These are parameters. Okay, so essentially, the parameter is is something that you can train in the training set, and hyperparameter is something you have to set. Okay, so basically, a model. So here we define the parameter and hyperparameter. Then we define a model. The model is basically you can think of that given for the decision tree, is that for example we find the maximum, or we define the maximum depth. Here you can see we define the maximum depth to be d. Okay, we define the maximum depth to be d, and then what are we doing in the training? So we are looking at a set. This set is all the H. H is the decision tree, and those H has the same depth. The depths of H are D. Okay, so basically we are looking at a set H. This H contains all the functions that has a depth of D. Okay, and what the training is doing? The training is searching in this H such that we can find the minimum training error. Okay, so the training, what training is doing is that we want to find the H in this H set such that the error of H and D train is the smallest. So this is what training is doing. Okay. So basically we want to find the H in this H set and such that the training error is smallest. So you can see that there are several things you need. So here you can see that we first need to define this D. We set the D, we get this H set. We get the H set, we can solve this optimization problem. Okay. So this H, I guess you didn't learn it. This is called functional space. Okay, 泛函空间. Okay, so it's a mathematical concept. Okay. Then we call this so it's a functional space, or in machine learning, this is called a hypothesis space. So basically, this is candidates. You think of this as candidates, right? Those H are good. I want to choose one from those H. I want to choose the best one to make my training error the smallest. Okay, so you can see that you remember that we cannot. So basically, the training error can be as small as possible, right? If we don't limit the H sets, if we ask the H to search from all the functions, then eventually the training error will become 0, right? So here, what we are doing is that we are limiting the space. We're limiting the space to the H set, such that we can control the ability, or we can control the complexity of our model. Okay. So then from this perspective, I think you can understand that the model parameter defines this H, and the hyperparameters defines this space. Okay. So here you can see that for decision tree, what are the hyperparameters? The hyperparameter is a depth, and what is a rule for tie breaking? What is a splitting criteria? Those are the hyperparameters, and the parameter is basically how to split. Okay, so similarly for KNN, so KNN is you can also imagine that we have a hypothesis set space. And those hypothesis spaces basically the nearest neighbor classifiers, and the KN does not have a parameter, okay, and the hyperparameter is K. So this is also a terminology I just mentioned here. So in the machine learning domain, we have different categorization of a machine learning method. For example, it's a discriminative model and generative model. And there's one classification, we call it a parametric model and non-parametric model. Okay. Parametric model means that this model contains parameters. Non-parametric model means this model does not contain parameters. So it's actually very interesting that there exists a lot of non-parametric models. I think all the model you have learned, most of the model you have learned is parametric. For example, linear regression is a parametric model because it has beta and alpha. Okay. So in the future, you will learn more non-parametric model. It's actually pretty interesting to learn those non-parametric model, because if there's no parameter, how you can learn? It's actually a very interesting question. Right. So if you're interested, you can search what are the representative non-parametric model. So it's very interesting. But recently, the non-parametric model was not very popular. Okay, because neural network is parametric. Okay, I think 10 years ago there was several years. During that time, the non-parametric is very popular, even more popular than the parametric model. Okay, so for the non-parametric model, usually they will come up with a very nice idea and also the very elegant mathematics. So people see a lot of paper at that time. Okay. So non-parametric, most of the non-parametric model is similar to KNN in that you just store all the data, and then in the testing stage, they just try to find a way to use the data, give you the answer. Okay. I think the very representative one was the kernel method. there's a group of method, they call it a kernel related method, kernelized method. Okay. So it's actually very elegant. If you want to learn some math, please read some paper on this. Okay, so here then we have the setting. So you can see that what I'm doing here. So now I'm trying to use notations to describe how the machine learning is trained. Okay, so here you can see that I have a data set that is D. This D is a combination of the training data set and testing data set. Okay, and we have different candidate models. This candidate model is basically, for example, this one is depth equals 2. This is depth equals 3. This is depth equals 10. Okay, so I define a depth, then I have a candidate space. I have a hypothesis space. Okay, so I can have m different hypothesis space. Okay, and then I can train the model. I can train the model using the training data set m times. I do the training m times for each. So this one has to be trained separately, right? So for the depth equals 2, you train this. For the depth equals 3, you train another one. So for each of the hypothesis space, you train the best model. H1, H2, H3, all the way to HM. Those are the best one in this hypothesis space. Okay, in the training data set. Okay, and then here you can see that one way I can do is that I can look at the testing data set. So I compare with this M model. So here you can see that I train M model in total. I compare this M model with using the test data set. Okay, and I pick the best one. Then I say this is my model I'm going to use. Okay, this is one way to do them. So this process, we call it a model selection. You can see that we are selecting the model. So this model selection is more like is selecting the hyperparameter, right? So actually you're choosing the optimal hyperparameter. Then you choose the optimal model. Okay. So it seems like this is very interesting. It's like a two-level computation. This level is like, for example, in each province, you have to wait in this province. And then each of the best one in this province, then you have to win another time, right? So for this one, you can train directly using our training method. Decision tree, you can train directly, or in the KLA, you train directly. But in the next level, because they're already trained, so you can never use the training data sets. Then they compare on the test. Okay, so that's one way to do the model selection. But there's actually an issue. After you do that, it thinks that you want to find the best model that is doing the best in the testing data set, right? So once you do this, you're finding the best model that works best in the testing data set. Okay, so potentially this step, this can also cause overfitting. Because you look at the testing data and you choose the best one for the testing data set. Then there's an issue. Your student didn't test the real unseen data. Okay, so our key idea, so remember that our key, what we care is a true error. So we don't know the true error, so that we are using the test error. The test error should be unseen. Otherwise, it cannot be representative to the true error, right? The test error should be unseen. Test data should be unseen. Otherwise, it does not represent the real error. Okay, but in this case, you can see that you see the test data because you choose based on the test accuracy, which is not valid. Okay, which is not valid. This is a typical we call it overfitting, or sometimes we call this a data leakage. This is a data leakage. Means that your test is leaked to the machine learning model. Then definitely your machine learning model will perform well in the test. Okay, so this is called a data leakage. This is kind of a data leakage. Okay. So this is a very common issue, very common error made in many papers. Okay, you go back to look at the AI papers in your domain, definitely you'll find some paper that do this. Okay, they do the model selection on the testing dataset. Okay, so this is actually a forbidden action. Okay, what we actually need to do is that we are introducing another dataset. We call it a validation dataset. So now we have training, validation, testing, 3 datasets. Okay, again, we have M hypothesis, and then we train this M model, and then we test, we compare those models in the validation set. So here we are using a validation set, and then we choose the best model, and then we use this best model to calculate the error in the testing dataset. So by doing this, the testing dataset has never been seen because you only see the validation set. You only not see the testing set. Okay, so this is a valid procedure. Okay, so training, validation, test. So you can see that we don't care the accuracy on the validation and test training. Okay, we only care about the accuracy on the testing dataset, and we need to make sure that the testing dataset is not leaked. Okay. Okay, so there's another way to memorize, to understand this is that the training data is for selecting the parameters. Training data is for parameters. Validation data is for hyperparameters. Okay. And testing is just for reporting the final performance. So in any cases, you shouldn't let your model be the testing data. Okay, otherwise it's an unfair comparison. Okay, so this is the idea, and so there's another approach. I shouldn't say this is approach. So basically, you can see that we have training, validation, testing, and there's actually a more rigorous one. Is that you still have training, validation, testing. So all the others are the same. So you'll find the best hyperparameter M. Okay, and here we add one more step. Is that or train a new model using both training and validation. Okay, then we can look at the performance for this new model. So why we are doing this? It's mainly because we think the validation model is a waste if you don't train it. Okay, so here you can see that after we decide the hyperparameter, we use all the data we can use for the training. Okay, so this one is a little bit different from this one. This one is only trained on the D-train, and here is trained on the D-train and D-validation at the final stage. Okay, so this is basically people just don't want to waste the data. Okay. Okay, so this is a typical model. This is we call it a model selection through the validation set. Okay, so I think there's an issue, and you also may notice that actually you don't have too many. In many cases, you don't have that many data. So here you can see that you have to make the data 3 parts. right? So that means that your training data becomes fewer and fewer, which is not a good idea. You want to have more data, otherwise your model cannot learn very well. Okay, then come up with a very smart idea called k-fold validation, a k-fold cross validation. The idea is as follows. So basically, you just select a k, and then you split the in. So here we're only talking about the training and the validation. We're not talking about the testing. Okay, testing is always leave away. Okay, so because testing is always used as the last time, as the final stage. So here we are talking about you have a data set. This data set is used for training and validation. And then what you can do is that you can split this data set into a part. Say for example, this we set k equal to 4. We split that into 4 parts. Okay, we call it fold. Okay, so k fold means that we will split into 4 fold. Then here we can see that we have fold 1, fold 2, fold 3, fold 4. Then what we can do is very straightforward. We can use 1 fold as validation, another 3 fold as training. Okay, we can do this once, and then we can do this another time. We can do so. Basically, we need to train the model 4 times. Okay, so let me be more precise. So given a hyperparameter, M, okay, then we train 4 machine learning model. The 4 machine learning model is basically this one as validation and this one as training, and this one as validation and this one as training. So basically, you use code 1, 2, 3, 4 as validation, respectively. Then you train 4 model. So this is so this is HM1, HM2, HM3, HM4. Okay, and your H1 will be you calculate the performance on fold 1. Or H2 M2 you calculate the performance on fold 2 because you train using you train using this, right? Then you calculate the performance on the validation. So you calculate the performance on the validation, right? So you have 4. You basically have the performance. You have 4 different performance, right? You take the summation or you take the average is the same. Okay, then you have the final validation error. So you have final validation error. It comes from all this 4 model. Okay, and a very interesting observation is that you validated on all the data. Okay, so this is fold 1, fold 2, fold 3, fold 4. You validated on all the data. Okay, and you use other data for training. You validate on all the data. So basically, after doing this, you have the validation error. Okay, so this is for one hyperparameter M. Remember that you have multiple hyperparameter. You do this for all the hyperparameter M. Okay, you do this for M equals 1, and you just try, for example, depth equals 1, depth equals 2. You do this again. So this is all one batch. You do this whole things again for another M. Then you try different M. You choose the smallest validation error for that M, for a particular M. Then you complete the model selection. Clear? Good. Okay. So you can see that question.
Okay. So in this case, the validation data will be seen for each setting for the hyper parameters.
Yes. Yes.
So will this cause the potential of overfitting?
No, because later so basically here so here you can see that you train here and you test here. So you always for this classifier, it's not saying this validation. So So you are still testing its performance on the unseen data. And here you also train here and you test here, you validate here. So you're also validating on the unseen data. So here, the performance, the validation error already talking about the performance on the unseen data. It's not on the seen data. We don't care about the seen data. Every time we only look at the unseen data. But here, because this is only for model for hyperparameter M. So later we have another M. We have multiple hyperparameters to test. Then we have to choose based on the validation error. So because of that, we see the validation error, we see the validation set. But it's okay because we have another testing set for the final testing. Okay, so here you can see that we do this whole things for one hyperparameter, and then we keep doing this for multiple hyperparameter. And then we choose the best one, the best validation error, the smallest validation error. Then eventually then what we are going to do is that, so after we do multiple times, we try multiple M. Then we choose the M star as the best one. Okay, so the M star achieves the smallest validation error. And then we train a H using M star and whole D. In this case, we don't need validation anymore because we already determined that we use M star. Okay, so here, this is the final model H, or the final model we will deliver. Okay, so essentially we submit this model for real world application, and we believe this is the best model that we can achieve. Okay, so this is a whole procedure that we're going. So remember, so here you can see that we never touch the testing set, because in reality you never know the answer of the testing set. So you have to develop. You think of a submission. You have to submit a model without knowing the testing set. Okay. Okay, so this is a full procedure for the k-fold cross-validation. You can see that the k-fold cross-validation maximally utilize the data. It's a little bit better than this one because we have a better validation error calculation. We actually use all the data for training, and we use all the data for validation. So this is actually more robust. Okay. So I skipped the notation. So later, if you are interested in writing some formulation on the analysis in your paper, please try to read more. So if you read more, you can write by yourself. Okay, but you can see that here. In general, we choose between M candidates, and this requires the machine learning training M times K times. And each of the candidates have to train K times. And you have M candidates, so in total, you are training M times K machine learning models. Okay, but and also there's another one. If you set K equals N, means that you have each of the data is one fold. This is possible. Okay, this we call it. This has a special name called leave one out. Leave one out means that every time you only use one data for validation, and then you use all the other data for training. Okay, so the leave one out is actually very precise. Okay, you can imagine every time you almost use all the data for training. Okay, just leave one single data for validation, but you do this N times. Okay, so I think you also notice what is the issue for leave one out. This is super time consuming. Okay, because this requires N times K training. Okay, so cross validation actually takes a long time. Okay, because this requires training a lot of times. But most of the machine learning method, this is actually, they already have a very good framework that can utilize parallel computing, those things, so that you can easily run this in your computer. Okay. if you are using traditional models, you have to do this. Okay. For example, using linear regression, decision tree, you have to do this because this will give you a performance upgrade. Okay. But for example, large language model, you can imagine this is impossible, right? So it has their own theorem why you don't need to do this. Okay. But for most of the machine learning, for example, decision tree, random forest, gradient boosting, those classic machine learning methods, this cross validation is extremely important. Okay. So maybe I say a little bit more on this. So in the scikit-learn, so if you want to play with this, you can see here we have a model selection part. Okay, so this I highly recommend you to read it. And for example, what we can do is we can do a grid search. Grid search means that given a for example, let me choose one. So there's a function called grid search cross validation. Let me see if there's an example. Okay. Okay, so this one. So here you can see that. So basically there's some data sets. Okay, so you don't need to know what is the data set, but basically you can see this is X and Y. And here, what you can do is that you can run a grid search, and your estimator is a SVM. SVM is short as supporting vector machine. You can also think of this as a decision tree. And then I need to specify a parameter grid. A parameter grid is something like this. It basically says that for this parameter C, I want to try 1, 10, 100. And for this gamma parameter, I want to try 0.01, 0.1. Okay, so how many parameter settings you need to try here? So you need to try 3 by 2, 6. Okay, so basically 1.01, 1.1, 10.01, 10.1. So that's why it's called a grid. It's basically something like this. Draw here. So grid search. So basically, here you can see that I have 1, 10, 100, and 0.01, 0.1. And then I have 6 combinations to try. Okay, so basically you have 6 combinations of hyperparameters to try. So that means you have to run 6 times. So the parameter m is 6, and then you need you also need to do a computer cross validation. So here it has a k-fold for some inner. So later you look at the. So here you can see that they are doing 4-fold. The split is 4. Okay, and by setting all those, you just run fit. You just input the x data and y data. This is basically our D. Okay, and you fit it, and this row, I think will run days if the data is large. It will run it, but it's okay. It just run days, and then you get all the answers. Then you can choose the best one. Okay, you can see that you can choose the best one, and then you can look at the performance of the best one. Okay, so you can see that even though what I'm describing is super complicated, but here is one line. Okay, because this very classic approach has already been written in these packages. Okay, so if you're interested, I highly recommend you to try. Okay, this is particularly important in classic machine learning method, but for deep learning, I think not too many. I think nearly almost no people will do this because our deep learning training is already complicated. You cannot do this anymore. Okay, but for decision tree, for those things, it's actually very simple to do this. Okay, so so the last page you can see here, it's just a summary. Okay, so you can see that for training, what you need to input is the training data set and hyperparameters. So here you can see that training cannot train the hyperparameters. And then this gives you the best model parameters under a hyperparameter. And then we need to do hyperparameter optimization. But this you need to input the validation data set, and then I give you the best hyperparameter. Okay, the cross validation is the same with the hyperparameter optimization, it also gives you the hyperparameter. And then eventually you can see that testing, you just submit a classifier, and then I finally take out the testing data, then I report the testing error. Okay, so here you can see that the testing is a hypothetical scenario that mimic the practice. Okay, you should never use the test data before testing. Okay. So this is a very serious issue. In particular, so this is very important in many cases. For example, in the past, many people they are using machine learning for the for stock to purchase the stock because they can predict the future price of the stock. And some people they this is real things that some people and even some company they develop a method, and they find that this method is pretty good when they test it. That they and then they actually they already then they just use it on the production, and then they find that this algorithm started to lose a lot of money. And then after this they start to look at this this thing, then they notice that there are actually some data leakage that made the performance be that good. Okay, so it's very tricky that some of your methodologies, for example, you try to develop some fancy approach so that you can publish a paper, but you should be very careful. Those approach, it has the performance gain is from your approach, it's not from your data leakage. Okay. Maybe I give you an example. That's some paper I think I reviewed. So what they are doing is that, so they have the X and the Y data. They are doing a supervised learning. And what they are doing is that first thing, they split the data to X test, Y test, and X train, Y train, and validation. Okay. And in their methodology, they think that if you can do a PCA of the model, of the data, then do you know PCA? Yes? I think PCA, you know that. If you can do the PCA of the X, for example, I can run a PCA for X. Okay, then I think this can boost up the performance. So what they are going to do is that they run a PCA in for X, and then they get the U sigma V. And then they use the U sigma V somehow in their machine learning model. Okay, so you can see that this is a data leakage actually. So somehow this, because they separate the data to testing later, but they're running the PCA for the full data set. They already leaked the data here. Okay, so this is very tricky. It's very, in many cases, the data leakage is very difficult to detect. Okay, but you should be very careful on this. Otherwise, your model will perform everything good on your paper, and then when you use it in reality, it becomes super bad. Okay. Okay. So I think I have to stop here. Slower than I thought. It's okay. I trying to cover some important issues in the supervised learning, but I think I don't have too many weeks to present to talk. Okay, but I think yeah, that's it for today. Later, I think later this week, or early next week, we'll release the first homework. Okay, so next week we'll continue on this, and I think there's a most important part I want to talk about. This is also a very PhD level. It's called learning theory. Okay, so I want to talk about this part. This part is very interesting. Okay. Okay, so that's it for today. If you have any question, let me know. Okay, so if you want to read some book, I would recommend a book called ESL. This is from Stanford. This is I think this is some Bible. This is a Bible for machine learning, called element of statistical learning. I don't know why this is called statistical. This one. Okay. If you're interested, you can read this the ESL. This is, I think it's a Bible for machine learning. And it's called statistical learning because it's trying to interpret the machine learning from a statistical perspective, okay, which makes it difficult. Okay, if you read a machine learning book, it usually won't be this difficult, but this one, it gives you a more mathematical perspective. Okay, but I think it's good for PhD students. You should have a concrete mathematical foundation for the machine learning method. Otherwise, you just use the method. Okay. Okay. So this one is open. Okay, so it's open online. You can directly download the PDF. Okay. So this is free. This is free. Okay, so that's it for today. I think most of the main things from this book. So if you want to, you know the concept here, and then you just go to the book to look at the full chapter. Okay. Okay, so that's it for today. If you have any question, let me know. Okay.